Hello everyone. In this lecture, we will use a technique we introduced last time about define branches of holomorphic functions to evaluate certain integrals, definite integrals through the residual theorem. More precisely, we will compute actually two integrals. So first one is integration of log x divided by x squared plus 1 dx and from 0 to infinity. Before we actually compute it, let's make a remark. So first, you have 0 is your singularity because your function is not well defined at 0, and infinity is an infinite region. So you should understand I in the following way. I is defined by limit epsilon goes to 0 positive, r goes to infinity, epsilon r log x divided by x squared plus 1 dx. Okay, then a natural question is why I exists. Okay. So of course, if you compute this explicitly as follows, you know it exists. But before that, in Math 521 or Math 522, we have some criterion to get this. Because why this exists? Because when x larger enough, then log x squared plus 1, this will be less than or equal to 1 over x 3/2. Okay, then by p test, this is integrable. Then integration of log x divided by x squared plus 1 dx exists. And when x, and also noted that when x pretty close to 0, then log x squared plus 1 is bounded by absolute value of log x. And now absolute value of log x, this from epsilon to log x, this we can explicitly compute the integral. So we just do integral by parts. You have negative x log x and plus, so of course epsilon 1 plus epsilon 1 dx. So this is negative. When you plug in 1, you get 0, and then when you plug in epsilon, you get this guy plus 1 minus epsilon. Okay, if you take limit, you have this is 1 because this goes to 0 if epsilon goes to 0 from right side. Okay, then you bound this integral, so this integral exists. So that's the reason why the integral exists, though it's not a Riemann integral. Okay, next we are going to compute it explicitly. So solution, we will introduce two methods. The first method is easier, but we still want to introduce the second one because second one teach you a lot of small techniques to estimate. If you do PDE, harmonic analysis, or Hala analysis, those basics are very important. You need to have the patience to really get through the messy. So method one, we first fix the holomorphic function. Here, a natural choice is fz equals log z divided by z squared plus 1. But then, of course, you have trouble. Log z is not well defined on the whole real number line. Okay, so you need to define the branch. So where the branch of the holomorphic function log z is defined by log z equals log r plus I theta, where z equals r e I theta with theta from negative pi over 2 to 3 pi over 2. So if you draw a picture, what we are doing, so on this complex plane, we cut the negative y-axis. The remaining part, on the remaining part, we can define z, and so the log, so it's defined by log r plus I theta, and the theta, the angle is from negative pi to 3 pi over 2. Okay, this is well defined, and then we need to construct a contour. So how to construct contour? Notice that here you have an essential singularity at the origin. Okay. Oh, sorry. It's not an essential thing. The singularity is not isolated. So the whole negative line is bad. You cannot define at all. Okay. And so you need, when you construct the contour, you need to avoid this. We already know how to avoid some point. Just do some detour. Okay. Then go this way. Okay, then take the contour to be the boundary of the indented up half disk. Okay, and then you need to figure out the pole. So look at cosine. So log z is holomorphic on the complex plane, getting rid of the negative y-axis, and the poles can only come from 1 over z squared plus I. Then inside our contour, you have pole I. Okay, and for simplicity, for convenience, we write down the contour explicitly. That's a boundary of the following region. Then by the residual theorem, we have integration x from negative r to negative epsilon log. So it should be log z over z squared plus 1, but then we use the formula in the green box to calculate this. So it will be log absolute value of x plus the angle is I. So for all the points here, angle theta is pi. Okay, so you plus pi I divided by x squared plus 1 dx. X is a real number. And then you have the small semicircle part. And noted that the angle, we just use I theta to denote this. So I squared exponential 2I theta plus 1 d epsilon ei theta. This is your parametrization. And then plus x from epsilon to r log x. Because it's on the positive real number line, the angle is 0. And plus theta from 0 to pi log r plus I theta divided by r squared exponential 2I theta plus 1 d rei theta. It's a bigger circle. The parametrization is the same, but the negative sign, noted negative sign comes from the clockwise orientation of the small semicircle. Okay, on the other hand, you have the residue 2 pi I, residue z equals I, log z divided by z squared plus 1. Okay, next we will compute each term, and let's denote the first as did I use notation? Okay, so let's denote this as I1, and the second one I2, third one I3, I4, and then last one I5. So for the I5, that's a residue 2 pi I residue at point I log z over z squared plus 1. So this is 2 pi I limit z goes to I log z divided by z plus I. Okay, then you plug in, you need to compute log z and record the green box here. So it had the real part is the log, the magnitude, and the imaginary part is the angle. Since I is on the positive imaginary number line, so angle is pi over 2. So, and the magnitude is 1, so log 1 is 0. Therefore, when you plug in, it's 2 pi I times pi over 2 I divided by 2I. So you have, this is pi squared over 2 times I. Okay, now let's look at I4. So it's an integral. You have two parts. So first part is log r divided by r squared exponential 2i theta plus 1 r e I theta times I d theta. And the second term is theta from 0 to pi I theta divided by r squared exponential 2i theta plus 1 r e I theta times I d theta. Okay, then let's bound the magnitude. So absolute value of I4 is bounded by the absolute value log r r squared exponential 2i theta plus 1 absolute value times r d theta plus the absolute value of theta times r squared exponential 2i theta plus 1 absolute value times r d theta. Okay, then for the first part, it's easy to see. It's bounded by it's O, capital O R log R. And then for the second part, it's log R over R. For the second part is capital O 1 over R. That is, it's bounded by some constant times 1 over R. Okay, now if R goes to positive infinity, I4 goes to 0. So that's the meaning of this sentence. Okay, next let's look at the first term and the second term, I2. So what is I2? I2 is integration from 0 to pi log epsilon plus I theta divided by epsilon squared exponential 2I theta plus 1 times epsilon I e I theta d theta. Similarly, you separate the two terms. The reason why we separate this is because sometimes so log epsilon and I theta has different growth rate when epsilon goes to 0. So when we separate them, we can use different method to estimate. Sometimes log part contribute, sometimes epsilon part contribute. This will be clear when we use second method to evaluate the error terms. Plus 1 times epsilon I e I theta d theta. Okay, then I2, the magnitude of I2 is bounded by log epsilon squared exponential 2I theta plus 1 epsilon d theta plus theta from 0 to pi theta epsilon squared exponential 2I theta plus 1 magnitude times epsilon d theta. Okay, now the denominator for this part, when epsilon is small enough, this is at least 1/2. So denominator is good. Therefore, the whole part, first half is bounded by epsilon log epsilon. Second part is bounded by O epsilon. So that implies that if epsilon goes to 0, I2 goes to 0. Okay, now let's look at first term, I1. So I1 is integration from epsilon to r log x plus pi I divided by x squared plus 1 dx. Okay, if you separate this, then you have log x divided by x squared plus 1 dx and plus 1 over x squared plus 1 dx times pi I. So I3, just integration from epsilon to r log x divided by x squared plus 1 dx. So the whole formula here implies that, let's denote this by delta. So, before the yellow part, we should let r epsilon goes to 0. Epsilon goes to 0, r goes to infinity. Then delta implies that the integration from 0 to infinity log x over x squared plus 1 dx plus from 0 to infinity 1 over x squared plus 1 dx pi I. So this is I1, the limit of I1. And for I2, we already know it's 0. For I3, it's the original real integral. And for I4 is 0. I5 is pi squared I over 2. Then compare both sides, we conclude further that the integral or log x over x squared plus 1 dx is 0, and the byproduct is the integral of 1 over x squared plus 1 dx is pi over 2, which is trivial because we have the antiderivative of 1 over x squared plus 1, that's a tangent x. So when you plug in infinity and 0, it's pi over 2 minus 0, which is pi over 2. So the byproduct is true, but for our purpose, we are done. We get the answer. Okay, this is the first method, which is pretty straightforward. You only need to estimate some error term, although it's not easy. Okay, next we introduce method 2, which is more involved. I suggest you at least to work on method 2 by yourself once in this course, because I do think it helps you to get some idea how to do estimate. No matter what are you going to do further, the hard analysis is useful. I mean, if you want to do some PhD program or whatever, this is a key ability. So consider fz equals log z squared over z squared plus 1. So don't ask me how do you think, why do you come up with these weird functions. So as I said, this method, the motivation of this method just want you to get some idea of how to do the estimate. If you only want to evaluate the function, the method 1 is most straightforward and intuitive. Okay, similarly, we need to define log z, but now we define log z in this way. We cut the positive real number line. And for the contour, as usual, we have first we have two poles, I negative I, and then we need to avoid the origin because it's not holomorphic. Okay, so we come up with the following contour. I will describe it more precisely when we write down the integral. So it's oriented in this way. So basically you have 4 parts. So first part is let's call it I1. So this is a horizontal part lie in the first quadrant. And then the integral is apply a residue theory. So the integral is from x is from 0 to r, capital R. I should say the radius is r, and the small radius is epsilon. So x is from 0 to r, and y is fixed to be epsilon for the horizontal interval in the first quadrant, log z squared over. We'll plug in the value of log z in the next step. So first step, we just specify the contour. And then next part, you have the bigger circle missing are small pieces. So this is given by the norm of z is r, but the absolute value of y is the imaginary part of the complex number, at least epsilon if x is positive. So in the right half plane, you're missing one piece. So this is a missing piece of the circle. You don't have this piece. Okay. And then the integrand is log z squared over z squared plus 1 dz. And then you have you have minus sign. Another horizontal part, but then the x is still from 0 to r, but the y is from the value of the imaginary part is negative epsilon. Log z squared divided by z squared plus 1 dz. And then you have the small circle, the half circle here. So this I2, I3, half circle here, I4, with clockwise orientation, so you have minus sign. And for this small circle, z is epsilon, and y let's see. X is so it should be x is negative. Okay. Log z square over z square plus 1 dz. And on the other side, you have the residue part. So the residue is taking at the first pole I, and then second pole negative I. Okay, so now let's estimate those terms. So I first denote this as I1, I2, I3, I4, I5, I6, and then I5, just a residue, is computed by 2 pi I limit z goes to I log z square over z plus I. And note that here, then we need to use the formula for log z. So log z is defined by this, log r plus I theta. Theta is from 0 to 2 pi. Therefore here, when you plug in I, log I equals pi over 2 I square divided by 2I. So this is negative pi cube divided by 4. And for I6, similarly, we have we need to compute log negative I square divided by negative 2I. And then recall here theta is from 0 to 2 pi. Therefore log negative I is 3 pi over 2I square negative 2I times 2 pi I. So this is pi cube, 9 pi cube over 4. Okay, now let's look at the second one, I2. So what is I2? We need to parameterize it because it's a bigger circle. So we parameterize by RE I theta. So it's integration theta from arc sine epsilon over r, because it's missing. It doesn't have the red part. So starting from epsilon sine epsilon over r, end up with 2 pi minus arc sine epsilon over r. And inside is log r plus I theta square divided by r square exponential 2I theta plus 1 dr e I theta. Okay, and here let's simplify a little bit. So the region for theta is given by this. Okay, probably I should say, let's estimate the magnitude of I2. And now, above, when R is larger enough, of course, its log r will be greater than I theta. So at least when I is large enough, you can bound this by 2 log r squared, and then this part can be bounded by r d theta, and then denominator will be at least 1/2 r squared exponent. So the norm is greater than 1/2 r squared when r is large enough. So 1/2 r squared. So this will be bounded by log r squared over r when r goes to infinity. It's clear this goes r2 goes to 0. Okay, next let's look at I4. It's another small circle. So here angle is from 2 pi over 2 to 3 pi over 2. And inside you have log epsilon plus I theta square divided by epsilon square exponential 2I theta plus 1 d epsilon ei theta. And now for the denominator, this at least 1/2, the norm of denominator at least 1/2, because when epsilon is small. Okay, then we can conclude this is bounded by epsilon log epsilon square when epsilon goes to 0. And the conclusion will be I4 goes to 0 if epsilon goes to 0. Okay, then the remaining two parts will be two horizontal lines, and to compute the horizontal lines, it will be, I think, will be the most difficult part of this method. So let's do it step by step. So R3, we first parameterize it. It's from x is from 0 to r, and you plug in y, then what do you have? You have log square root x squared plus epsilon squared and plus I 2 pi minus, because I3 is a horizontal line in the fourth quadrant, so the angle is a little bit less than 2 pi. So by the definition of log z, so here we use this formula. X minus I epsilon square plus 1 dx, and then the first one is given by x from 0 to r log x squared plus epsilon squared plus I arc sine epsilon divided by square root x squared plus epsilon squared divided by x plus I epsilon square plus 1 dx. Okay, now we need to compute I1 subtract I3, and this is given by integration from 0 to r. I just copy two formula and expand the numerators. So log square x squared plus epsilon square plus I arc sine epsilon x squared plus epsilon square plus 2I arc sine epsilon divided by x squared plus epsilon square times log square root x squared plus epsilon square divided by x plus I epsilon square plus 1 dx, and minus 0 to r log square root x squared plus epsilon square plus 2 pi I square plus I negative arc sine epsilon divided by x squared plus epsilon square times log square root x squared plus epsilon square plus 2 pi I and plus I arc sine epsilon divided by x squared plus epsilon square divided by x minus I epsilon square plus 1 dx. The reason why we want to do this is because we want to cancellate the arc sine part with the arc sine part and the log square part with the log square part. Although not exactly cancel, but you cancel the main contributions. Okay, then you do the following. You further expand this part. And what do you have? You have negative from 0 to r log. You first take out 2 pi I square divided by x minus I epsilon square plus 1 dx minus 0 to r 2 pi I times 2 times log square root x square plus epsilon square divided by x minus I epsilon square plus 1 dx, and then you have log square root x square plus epsilon square over x minus I epsilon square plus 1. So let's write one more step. Plus, so plus is from 0r log x square plus epsilon square 1 over x plus I epsilon square plus 1 minus 1 over x minus I epsilon square plus 1 dx, and then what do you have? Then you have something involving arc sine, so plus 0 to r I arc sine epsilon over square root x square plus I epsilon square plus 2 2I arc psi epsilon divided by x squared plus epsilon squared log square root x squared plus epsilon squared divided by x plus I epsilon squared plus 1, and then minus x from 0 to r I negative I arc sine epsilon divided by x squared plus epsilon squared. Okay, and times log square root x squared plus epsilon squared plus 2 pi I divided by x minus I epsilon squared plus 1 minus 0 to r I arc sine epsilon divided by x squared plus epsilon squared divided by x minus I epsilon squared plus 1 dx. Okay, now we need to estimate term by term, and so we call this as J1, J2, J3, J4, J5, J6, and for J1, J2, we leave it as it is, because later on when we let epsilon goes to 0, r goes to infinity, we get what we want. And then for J3, we computed explicitly. This is J3 is this part. So you compute the difference here. It's integration from 0 to r log log square root x squared plus epsilon let me look at it. Yes, and square and the times so when you do subtraction, you have negative 2x I epsilon divided by x plus I epsilon squared plus 1 times x minus I epsilon squared plus 1 dx. And now we want to estimate its limit when r and epsilon goes to 0. So our purpose is is to show that the limit is 0. But now currently we have no control it because analysis. Log square root x squared plus epsilon squared has two gross aspects. That is firstly, when x is close to 0, this has a behavior log epsilon squared, which is log epsilon. And when x is greater than 1 largely, then this has a feature as log square root of x squared. Okay, that motivates us to separate the integral as follows. From 0 to epsilon, the same integrand. Okay, it should be 4, sorry. and log square root x squared plus epsilon squared divided by x plus I epsilon squared plus 1, x minus I epsilon squared plus 1, and plus epsilon to r minus 2I epsilon 2x log square root x squared plus epsilon square divided by x plus I epsilon squared plus 1, x minus I epsilon squared plus 1 dx. Okay, then for the first part, the denominator is good. So those denominator is bounded, for example, by the norm of the denominator is bounded by 1/2 when epsilon small enough. And then for the numerator, x is bounded by epsilon, and this one is bounded by log epsilon absolute value. Okay, so totally the first term gives you O epsilon log epsilon. Okay, then for the second term, it's a little bit more involved, but we can still do that. So for the we first estimate the the denominator. So for this part, norm of x minus I epsilon squared plus 1 is 1 plus x squared minus epsilon squared minus 2ia x epsilon squared. So this will be greater than 1 plus x squared minus epsilon squared. Same thing for the previous one. So it will be bounded by, so the absolute value of the second integral will be bounded by, you copy it first for the denominator. It's 1 plus x squared minus epsilon squared, and also for the log part, for the log part, we can, because let's do it step by step. So now we consider log square root x squared plus epsilon squared. So when x is large enough, then this will be bounded by log x squared plus x squared. So here when x, for example, when x greater than 1. But when x is small, then this is negative. So the log part is negative. And if you take absolute value, this is negative log part. Okay, so this should be bounded by this is less than log square root of x squared. Okay, so totally it will be bounded by log x absolute value plus 1. plus log 2, just a constant. This is log x plus log 2, square root of 2 dx. Okay, so this is analysis for the log term. Then we need to evaluate this part. So let's repeat it. Let's write it again. So epsilon to r, absolute value of this minus 2i epsilon times 2x log x plus log square root 2 divided by 1 plus x squared minus epsilon square dx. Okay, then we separated these two terms, log x and log x and log 2. So this is less than epsilon to r 4 epsilon x times log x absolute value divided by 1 plus x squared minus epsilon square dx, and then you have absolute value. Actually here you don't need to have absolute value anymore. It's always positive. And then plus from epsilon to r 4 epsilon x log square root 2 divided by 1 plus x squared minus epsilon square dx. Okay, then what we do is we separate further from epsilon to 1 and for epsilon x log x divided by 1 plus x squared minus epsilon square dx, and from 1 to r for epsilon x times log x absolute value divided by 1 plus x squared minus epsilon square dx, and then plus from epsilon to 1 for epsilon x times log square root 2 divided by 1 plus x squared minus epsilon square dx, plus 1 to r for epsilon x times log square root 2 divided by 1 plus x squared minus epsilon square dx. Okay, then look at the first term. This part is bounded and the interval is less than 1, so the whole thing is O epsilon. And then for the second part, when x is large enough, you can omit. Okay, so for this part, is bounded by 4 epsilon integration 1 to r x log x 1 plus x squared over 2 square dx. So this integral is bounded because your denominator is quite large. It's degree 4, but the numerator only degree 1 plus epsilon. So the whole thing is still O epsilon. Okay, and similarly, for this part, this is bounded, and therefore it's O epsilon. And for this part, by the same argument, it's less than 4 epsilon times 1 integration 1 to r x log square root 2 1 plus x squared over 2 square dx. This is bounded. Therefore, it's also O epsilon. Okay, now we turn back what we have. Eventually, we show that the yellow part is O epsilon. Therefore, J3, a small conclusion, J3 goes to 0 when epsilon goes to 0 plus and R goes to infinity. Okay, and the next we want to estimate the J4. So recall what is J4. J4 is here, and so we copy it first. So J4 is integration from 0 to R I arc psi epsilon divided by square root x squared plus epsilon square plus 2I arc sine epsilon divided by x squared plus epsilon squared log x squared plus epsilon squared. So let's double check if it's correct. Yes, and divided by x plus I epsilon square plus 1 dx. Okay, and let's do some analysis. Here, the hard part is arc sine and the log square root x squared plus epsilon squared. And for this one, when the argument is small, or when this is small, so arc sine, this function is bounded by 2 times epsilon x squared square root x squared plus epsilon squared. So this is a good estimate. Okay, so now when this will be small, so x is if x is greater than epsilon largely, then this will be small. Okay, on the other hand, so the other direction, if the argument is large, but relatively large, of course it's bounded by 1, it's large, then we have a little bit worse estimate. This is bounded by, for example, pi, or pi over 2. It doesn't matter. So that suggests that we need to cut the interval from 0 to R by some number larger than epsilon, but not that large, because for log part, you need to have some kind of epsilon there. So that motivates us to take the cut square root epsilon plus square root square root epsilon to r, and then the integrand is the same, I arc sine epsilon divided by square root x squared plus epsilon squared plus 2I arc sine epsilon square root x squared plus epsilon squared log square root x squared plus epsilon squared divided by x plus I epsilon squared plus 1 dx. And you copy it again. Square plus 2I arc sine epsilon divided by x squared plus epsilon squared log square root x squared plus epsilon squared divided by x plus I epsilon squared plus 1 dx. Okay, now for the first part, we have the following estimate. Let's call it J41. So the magnitude of J41 will be less than or equal to, now you can, for the denominator, this will be bounded by 1/2 in its magnitude, and for the numerator, then you see it will be bounded by integration from 0 to square root epsilon, some constant, I missed that, some constant times epsilon squared divided by x squared plus epsilon squared plus epsilon x squared plus epsilon squared log square root x squared plus epsilon squared divided by 1/2. So it can be absorbed into the constant dx. Okay, now let's do use substitution. Let x prime equals square root epsilon times x equals square root epsilon times y. Then the integral is 1/0 to 1 c times epsilon square epsilon y square plus epsilon square plus epsilon y square plus epsilon square log epsilon y square plus epsilon square square root dy. So square root epsilon dy. So it's some constant times epsilon divided by y square plus epsilon plus 1/y square plus epsilon log epsilon log epsilon square plus log square root y plus y square plus epsilon. You can take the absolute value, square root epsilon dy. Okay, and when epsilon goes to 0, so this of course is bounded by 2 log square root epsilon, also value square root epsilon you have here. Okay, and for this part, of course this is bounded by, do I make some mistake? Okay, yeah, I see. these two are together. Okay, and then you have the square bracket. And of course, this will be less than integration from 0 to 1. 2 log some constant we can omit to. So this will be less than this. Okay, in magnitude. So we have log square root epsilon, so value y squared plus epsilon square root epsilon dy. Okay, let's see if we can bound this guy. So first, what is the integration of 1 over y squared plus epsilon dy? We do use substitution. Y is square root epsilon x, and then you have 0 to 1, 1 over epsilon x squared plus 1 d square root epsilon dx. Here will be 1 over square root epsilon. So then you have 1 over square root epsilon arc tangent x, 1 over square root epsilon to 0. Oh, then that tells you it's not enough. So this part, when you plug in, it's not enough to conclude this goes to 0. That means we need to make our estimate sharper. That's the usual situation we met when we do estimate. Sometimes the cut is not enough. We need to have some better way to control it. Okay. So how to deal with this part? Minus plus. So first we need to understand where's the problem. So the problem is the first part is good. This part is always good. You already see from the estimate. This part is good. So we need to bound. It's not enough. So we need to bound which one? We need to bound the second integral. So here. Oh, not this one, the original one. From 0 to square root epsilon and 2I arc sine epsilon divided by square root x squared plus epsilon squared times log square root x squared plus epsilon squared divided by x plus I epsilon squared plus 1 dx. So how to bound this? Of course, here for the denominator, you can drop it. So this is bounded by integration from 0 to square root epsilon times some constant and arc sine epsilon divided by x squared plus epsilon squared times log square root x squared plus epsilon squared divided by 1 plus x squared minus epsilon squared plus 2ix epsilon squared dx. Okay, oh sorry, the denominator is dropped. Okay, then for this one, do we have some? Oh, I see. Now you use this substitution. Use substitution. Let x equals epsilon y. So the integral will be from 0 to 1 over epsilon y, and arc sine 1 over square root y squared plus 1, and the log, and here you have epsilon plus log square root 1 plus y squared absolute value divided on, that's it, dx. Oh, sorry, d epsilon dy. Okay, now all you need to do is bound this guy. Of course, you can separate this into two parts. Arc sine 1 over square root y squared plus 1 times log epsilon times epsilon dy, and then the other term is from 1 over square root epsilon arc sine 1 over square root y squared plus 1 times log square root 1 plus y squared epsilon dy. Okay, and then for the first term, this part, this is bounded, so this will be less than 1 over square root epsilon times log epsilon times epsilon. So this is bounded by square root epsilon times log epsilon. Okay, and then for the second one, when epsilon is, so you separate this further, this can be written down as integration from 0 to 1 plus integration from 0 to 1 over square root epsilon, and the integrand is the same, arc sine 1 over square root y squared plus 1 times log square root 1 plus y squared times epsilon dy. And then for the first integral from 0 to 1, of course, it's bounded by epsilon, so O epsilon. And for the second one, we do some estimate. We can change log square root 1 plus y squared by log y plus log 2 times some constant 2, for example, some constant c. And for the arc sine part, we can bound it by also by a constant times 1 over square root y squared plus 1 and times epsilon dy. And then from this, it's clear that okay, let's make it this is, so for this part is less than 1 to 1 over square root epsilon log y divided by, we don't like this, so we change it to y squared square root over 2. So it's y times some constant and epsilon dy plus 1 over square epsilon 1 times a constant times 1 over y times epsilon dy. Okay, then the second term, what is this? You can integrate this and got this is O epsilon log square root epsilon, which is O epsilon log epsilon. And for this term, actually you can bound it by log y is bounded by log 1 over square epsilon, and then you can integrate 1 over y. That gives you log square epsilon, and then you have epsilon. So totally it would be bounded by omega log epsilon square. Okay, so finally, conclusion. So let's go back. Are we done with J4? Yeah, we get J4 1 goes to is over the size O epsilon log epsilon square at most, and in particular J41 goes to 0 if epsilon goes to 0 plus. Next, we want to estimate J42. So we copy it here. J42. What is J42? It's the same thing, but now it's from square root epsilon to R I arc psi epsilon divided by square root x squared plus epsilon square plus 2I arc psi epsilon divided by x squared plus epsilon square log square root x squared plus epsilon square divided by x plus I epsilon square plus 1 dx. How to estimate this one? So first we I see. Yeah, probably in J41 you can replace the arc sign just by constant. It might simplify your calculation. Okay, but anyway, so this time so let's go back to this. Oh, I see. For J41, sorry, for J41, it's much easier because here this is bounded by constant, this is bounded by constant, this is over size log epsilon. So totally it's square root epsilon log epsilon of this size. Yes, although our estimate is better, but for the purpose of the vanishing conclusion, you don't need to be that sharp. Okay, and now for this one, we can plug in take the absolute simple. This will be less than or equal to separate epsilon square root epsilon r epsilon x squared plus epsilon square times some constant square. So you have this. And the denominator is 1 plus x squared minus epsilon squared. You just omit the imaginary part. Epsilon square root x squared plus epsilon squared log plus epsilon squared. Okay, now for the first part, so we separate into two parts, constant square root epsilon r epsilon square x squared plus epsilon square 1 plus x squared minus epsilon square dx plus c times square root epsilon to r epsilon divided by square root x squared plus epsilon square 1 log square root x squared plus epsilon square absolute value divided by 1 plus x squared minus epsilon square dx. Okay, then let's integrate this part. You do the u substitution, let x to be actually you can drop epsilon square, so replace this by half x squared over 2, 1 plus half x squared over 2. Okay, so you have epsilon squared over x squared times 1 plus x squared over 2 times some constant. And of course, this integral is of order at least O epsilon. Okay, and then for the second part, the denominator you can also drop it to 1 plus x squared over 2, and then for the numerator you have log either log x absolute value plus log 2 or log x. So you can replace this by this quantity. Okay, so next, so this is bounded by constant times square root epsilon r epsilon divided by x squared plus epsilon squared times 1 plus x squared over 2 divided by log x plus log 2 dx. And then you also cut it into two pieces from epsilon to 1, square epsilon to 1 from 1 to r. And for the first subinterval, so for the first subinterval, it's bounded by epsilon times the integration of 1 over square root x squared plus epsilon squared times 1 times constant and the log log x plus some constant dx. And then if you use U substitution, you have x is epsilon y, then you have this is 1 over epsilon, 1 over square root epsilon, 1 over epsilon times 1 plus y squared, and the log epsilon plus log y plus c times epsilon dy. Okay, then you cancel out epsilon with epsilon, and then the whole thing will be bounded by it's O epsilon times log epsilon. And then for the second part, you just replace 1 plus x squared kind of by x. Okay, so it's bounded by integration from 1 to r epsilon x times log x times some plus some constant divided by 1 plus x squared times some constant. And this is epsilon times constant times the integration of log x plus some constant and the x cubed dx. Since this is bounded, so the whole thing will be O order. O epsilon. Okay, then we finish the estimate for J42. So conclusion, J42 is at least O epsilon log epsilon. At most O epsilon log epsilon. So J4 goes to 0 if epsilon goes to 0. Okay, we do spend a lot of time on this, and then similarly, 1, 2, 3, 4, 5, 6. Similarly, you can do the estimate. You can do J5 in a similar way. Okay, similarly to J4. J5 is, I can write down the answer here. Probably, if you have interest, you can work on this. Epsilon log epsilon. Of course, you have final estimate, but this is enough for our use. And then for J6, you still use the cutting, and then you do the estimate. It's square root epsilon. Okay, and then take the limit. R goes to power to infinity, epsilon goes to 0 plus, and then we conclude the limit and the limit. The first term I minus 3 equals, so because the first term we didn't, J1 we didn't do anything, so now we just write down the J1. J1 is 4 pi squared over x squared plus 1 dx. And the J2 is negative 0 infinity 4 pi I log x divided by x squared plus 1 dx. We get the same answer as method 1. Okay, we're done here. So the homework, I really suggest you to do the homework. Write down all the estimates for J2, sorry, J3, J4, J5, J6 explicitly by yourself. Okay, I think it's a good exercise, and you see how I manage this. If you have some trouble, some estimate cannot be done, you just cut the domain to pieces. Okay, I will stop here.